Hi everyone, and welcome to section 3.2, on conditional probability. Now, this chapter 3, I think I've said before, this is one of the more intense chapters in the entire course, and certainly one with the most mathematics, and things can get a little difficult for some students. When students do struggle in this course, it's usually with this chapter. So we talked about basic probability and some counting techniques. Now we're going to see talk about conditional probability, which is how certain events can affect the probability of other events. And so I'm going to give you a bunch of examples first before we give you some definitions. So I probably, a lot of you are either Bears or Packers fans. So suppose the Bears and Packers are playing a football game, and incidentally enough, the Bears and Packers are actually playing a game today as we're recording this video. Well, we'll consider the three events. The A is the event that the Bears win. C is the event that the Bears lead by 21 points with 30 seconds to go. And C is the event that the Chiefs beat the Raiders. Now, the thing is, it could be that the probability, before the game starts, it might be that the probability of the Bears winning might be around 50%. Okay? Especially if the teams are well matched. However, if the Bears happen to lead by 21 points with 30 seconds to go, I don't think any team has ever lost a game when they're leading by 21 points with 30 seconds to go. So whereas the probability of A happening is about 50%, if B happens, the Bears are almost certain to win. So we would say that whereas the probability of B happening might not be that great, okay, but if it is happening, then the probability of A is very close to 1, okay, or 100%. Okay, so B does affect A in the sense that if B is happening, A is almost certainly to happen. Okay, so we could say maybe the probability of A was about 50% or 0.5, but the probability of A given that B is happening is almost about close to 1. Okay, and okay, now C though, this event the Chiefs beat the Raiders, these are completely two different teams, and they shouldn't have any effect on the game at all, right? The Bears game, right? So the probability of A happening given C, maybe the Chiefs and Raiders played the previous day, that shouldn't have any effect really on the Bears game. So the probability of A given C is still going to be probably about 50% or 0.5. Okay. These are we would say that A and C, since C has no effect on A and A has no effect on C, we say that A and B would be independent, and B and C, or A and B, would be dependent, because we would say that B certainly has an impact on A. Okay. All right, and of course B. We should also check that B and C are also independent, right? Because they shouldn't have any effect on each other. All right, let's look at another example, a more familiar one with coin tossing. Let's say a fair coin is tossed 3 times, and we already wrote down the sample, all the possible outcomes. This is the sample space of this experiment. And let's say A is the event that the third toss is a head, B is the event that the first and second toss is a head, and C is the event that all 3 tosses are heads. Okay, now Are A and B independent of each other? If the first and second tosses are heads, is it more likely that the third toss will be a heads or a tail? Well, really, we know intellectually that the first and second tosses should have no effect on the third toss, right? We might think maybe in our minds, if we have some money on this, that if let's say if we're betting on tails, we would say, oh, okay, well, tails is due, but no, it's we know, but in reality, the first, second, and third tosses are all independent of each other, and we can see that here. Because we can see that there are, like, the probability of A happening, given that the probability of A happening would be 1/2, and the probability of the probability of A given B, given that B has happened, as the first and second heads are tosses. Well, if we're just looking at this little, if we just restrict those are the only outcomes where the first and second tosses are heads, and we can see exactly 1 out of 2 of them will have the third toss being a head, right? So this is still going to be 1/2. Right. Now, let's talk about the other thing. The probability all 3 tosses are heads. Well, there's only 1 out of 8 possibilities where this happens, so the probability of C would be 1/8. But let's say if we wanted to talk about the probability of C given B. Well, now, given that however unlikely B was happen, the probability of B was actually 1/4. But given that it's already happened, then we're only one more head or one more toss away from C happening, right? So this would actually be 1/2, because again, in the case where B, the event B corresponds to this subset. And there's exactly one of those 2 situations where C happens. Okay, so these are examples of conditional probability. Okay, the given part. We can say that in this case we would say that A and B are independent, but B and C are not. Or we would say they're dependent. They affect each other. Okay. Maybe one more example here before we get into some definitions. Let's say we have a jar with 3 green balls and 3 red balls. Okay, and 1 ball is selected and removed, and then a second ball is selected. And let's say A, B, C, D are the events that the first ball is green, the second ball is green, the first ball is red, and the second ball is red. Okay. So let's take a look at what would be this would be, if we wanted to find the probability, the probability of B, of course, the probability of all of these events by themselves is 1/2. Because you're talking, in both the cases, you're just taking certainly the probability of A and C would be 1/2. And the probability of B and D, if we don't have any information about what the first ball is, the probability of B and D would be 1/2 as well. Okay, if you were to write down all the possible outcomes, you would see the probability of all these events is 1/2. Okay, but let's take a look at what would be the probability of B given A, let's say. So if A happens, that means we have, here's our jar. Okay, we did have three green balls, but now we only have two. It's like G1 and G2, and then we have 3 red balls, R1, R2, and R3. Okay, so this is after A happens. We're in this situation. And so the probability is that what's the probability of picking green ball? It would be 2 out of 5. So the probability of B given A would actually be 2/5. Okay. And the probability of, let's say, D given A, okay, well, we can see that there are 3 red balls out of 5 total balls, so this would be 3/5. Okay. So we can see that A does affect the probability of B and D. So once again, we can see that A and B, these are dependent, and also A and D are dependent. We can also see that if we wanted to find I'm sorry, this should be the probability. Sorry about that. The probability of, let's say, let's say B given C. Well, if C happens, then we have first ball is red, so then we only have 2 reds here and 3 greens. Okay, so the probability of that the second ball is green would be 3/5, and the probability of B, of D given C, that D is the probability that the second ball is red, that would be 2/5. Okay, because we are in this situation. Okay. So these are examples. So we can see that A and D are dependent. A and B are dependent. B and C are dependent, and C and D are dependent. Okay. These are all examples of dependent events. The probability of one event, the occurrence of one event affects the other. Okay, so that's kind of an illustration of what we're getting into. And in the second video, I'm going to show these, give the definitions, and do some more examples.